Hello, this is Zaman, and I will record the week 10 contents. There are total 7 questions, and our topics is the directional derivative, classify stationary points, maximum rate of change, extreme points, and Lagrange multipliers, and Taylor approximation. Here is a simple definition of a stationary point. So a stationary point of a function f of x is a point where the derivative of f of x is equal to 0. So we need to remember that. A saddle point is a point where x0 and y0, so we can write down x0 and y0, where f of x, like f of x and x0 and y0, is neither a maximum nor a minimum at that point. So since we discussed the extreme points, so what is the extreme points? In the point of mathematics, extreme point is a point in a convex set that does not lie in any open line segment joining 2 points in the set. Before starting solving the problems, we need some theoretical discussion on directional derivative. So in directional derivatives, we can use like a du hat. So this is a unit vector u, and this is a directional derivative of a unit function is like du hat f of x x y a plus f of y x y b. So we needed this formula to solve the problems. And there is some examples. If you have the unit vectors is here, and how to calculate is like directional derivatives. And this is the directional derivative will be, if you have the unit vector cos theta and sin theta, then directional derivative will be f of x, f x y cos theta plus f y x y sin theta. Okay. Then maximum directional derivatives. So maximum directional derivative, the theory says the max value of directional derivative is the magnitude lambda f of x. This occurs when unit vector is in the same direction of lambda f of x. So duf and nabla f of x dot au is this is called is a norm of nabla f of x times norm of u cos theta. So maximum occurs when theta equal to 0. The maximum value of directional derivative is this. So theta equal to 0 means the unit vector u is in the same direction of nabla f of x. So this is important when the maximum directional derivative will happen. So maximum or minimum of a function f of x subject to a constraint of the form gxy equal to k. This is max or min, max or min f of xy. So subject to g of xy equal to k. So then you needed to use the method of Lagrange's multipliers. So find all the values of x and y and lambda such that lambda f of x equal to lambda g of xy, and g of xy equal to k. So we need it in this part. This formula, remember that this is from the constant optimization. And the Taylor expansion for single variable functions. We have two equivalent representation of the Taylor expansion for single variable functions. And this is the f of x. This is the formula, f of x plus delta x. So delta x is very small value of x. So very small value, it is increment. So x plus delta x, f of x, f prime of x, delta x, f a double prime of x divided by 2 factorial. So this is a factorial sign, remember that. factorial sign plus dot 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 dot. So we can write down this way as well in the summation. So f x plus delta x equal to summation n equal to 0 to infinity f power n f x n factorial in bracket delta x power n. So zeroth approximation is x plus delta is approximately f of x. First approximation is x plus delta x. Approximately is like this is equal and approximate f of x plus a prime of x delta x. Second approximate similarly f of x a prime of x delta x a prime x 2 factorial and delta x square. So Taylor expansion for multivariable function. If you have a variable, it's like a z is a dependent on x and y, then z can be write in terms of a function z equal to f of xy. So Taylor expansion of this function will be like this: f of x plus delta x and y plus delta y, f of xy plus f of x xy delta x, f of y x plus delta y plus 1 over 2 f x x. So you have to derivative the functions 2 times with respect to x. And here x squared 2 f xy delta x and delta y plus f of f. You need to derivative the function with respect to y in 2 times, and then y f y y x comma y delta y squared plus dot 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 dot. So this is the square bracket term. So you can see is jf lambda. So round parenthesis term, we can write down this one. So expansion can be write down for multivariable function f of x plus delta x, y plus delta y equal to f of x, y plus jf delta plus 1 over 2 delta power t and hf delta plus. So mainly we need this part to remember in that case. Okay, we have to remember. So here they have given different approximations, same as the single variable function. We need this part actually. So this is expansion of f of x, and this is called the f of x y at the point a b. So f of x y equal to f of a plus a comma b plus f of x a b x minus a plus f of y of a comma b y minus b, and 1 over 2 x minus a and y minus b. This is Hessian matrix f of hfab x minus a y minus b plus dot dot dot. So this is a Jacobian and Hessian. So hf is a Hessian matrix. This way you can write down, and the Jacobian jf delta f delta. I mean this is a partial from differentiation. So delta f by delta x and delta f and delta y. So note that delta f equal to j power t and f. Hessian is a symmetric matrix, remember that. And classify of the stationary matrix is the D equal to determinant of Hessian matrix. So we need the directional derivative, this formula at this moment. And remember the directional derivative when would be the maximum when theta equal to 0. And method of Lagrange's multipliers, we need this formula. Okay, so this is Taylor expansion. This is the formula. And from there, this is Taylor expansion for the multivariable functions, same thing. And this is, we need the Jacobian of f. What is that? what is the Hessian matrix, how to find the Hessian matrix. So now we will start the first problem here. Find the directional derivative at the given point in the given direction. And the problem is given here, f of x, y equal to x square root y. The point is 2, 4. And a vector is given equal to 5i and 10j. The solution is here. You can write down first the directional derivative formula. So du f of av equal to, this is a nabla, this is a Greek word nabla, f av, this is a transpose t, and dot product u unit vector. So what would be here? A del nabla f x y is f x x y, and f, would be derivative with respect to x, sorry, y, x comma y. So then if you look at that, if you derivative this function with respect to x, that will give you y, and this one will give you x, y. Okay. Now, at this point, what will happen? Never f2, 4, that will give you 4, and 2, 2, 4. That's mean is 2 on over 2. So we have that. And look at that is here. U is not a unit vector. It's not a unit vector. So we need to make a unit vector. So what would be happen? How to make a unit vector? So like this, u hat and this vector and norm of that vector. So here, look, this, the norm of this is 2, is 5 square plus 10 square. So that will give you 125. So 5 over square root 5. So 1 over 5 square root 5, and this one. So this is your unit vector. Okay. So finally, we have the unit vector here. The mistake is here. This should be 5, and this should be 10. So 5 over 5 root 5 I plus 10, 5 over root 5. This is j. So you can write down what this cancelled. So this is a 2. So 1 over 5 square root 5i plus 2 square root 5j. And this is the unit vector. So once you get the unit vector, then you have to apply this formula. So you have this part. So you need to just transpose of t, this one, you can do it easily. And what else we have? So write down this formula here. Du f24 equal to 2 on over 2 transpose this t and the u vector, this one. So 1 over square root 5 and 2 over square root 5. So this is your, if you do the multiplication is here, so that will give you 2 times 1 over this plus 1 over 2 and 2. This is a plus square root 5. So 2 square root 5, and this is 2 is cancelled. So 1 over 5. So finally you have 3 over square root 5. So look at that again. So the directional derivative formula is this. You need nabla f xy. So f need to be derivative with respect to x and with respect to y. And then you need to plug the point in that, the matrix. Then you will get this matrix. And if U is not a unit matrix, then you need to make it unit matrix. So if you divide the U vector by the norm of the U vector, then you will get a unit vector. Once you get the unit vector, you need to plug all the information here that we have did it exactly. So this is your final answer. This is your answer. Okay. Now we have second question. Find the maximum rate of change of f at the given point and the direction in which it occurs. Mhm. So the maximum rate of change at AB, let's write down maximum rate of change at AB is, the norm of nabla F AB. So this is called the double partition. The direction of the maximum change is direction of the maximum rate, maximum changes is nabla F AB. So here, basically, you need to find out nabla F X Y. So F of X X Y and F of Y X Y. So if you derivative this function with respect to x, then you will get 4y and 2 square root x. So write down 4y, 2 square root x. And then if you derivative with respect to y, the same function, you will get 4 square root x. So this is the thing. Now, you need to find out the direction of the maximum change at the given point. The given point is 4, 1. So write down the maximum, the direction of the maximum change is 4, 1. So if you, this one at 4, 1, we have like this, and 4 times 1. So this is 4, and 4 square root 4. So you have basically 1 and 8. So the maximum rate of change is, this is the maximum rate of change maximum rate of change is one square plus 60 square. So you have 1 plus 64 square root, so square root 64. So this is your answer. So if you get if you asked to find the maximum rate of change, then just remember you need to find out the norm of nabla f of AB at the given point. So how to find out the direction of the maximum change is nabla f of AB. That means nabla f of xy equal to f of x, xy, f of y, xy. So find out the derivative of x, derivative of y, and then you will get this matrix is like this. Okay. So next question we have, question 3. Find and classify a stationary point. So this is two problems is here. So find the class stationary point. We need to derivative like f of x with respect to, if this function need to be derivative with respect to x and with respect to y and set equal to 0. Okay. So our function is here f x y. This is a number 1. X power 3 minus 3x plus 3x and y power 2. So if you derivative with respect to x, you will get 3 x power 2 minus 3 plus 3y squared. So this is your equation number 1. And if you derivative this function with respect to y, you will get is 6xy. This is your equation number 2. And from equation number 2, if you set this function equal to, the derivative, the first derivative of the function equal to 0, then you will get is f of xy, so which is 6xy equal to 0. So from here you can see easily x equal to 0, 1, y equal to 0. If x equal to 0 from equation 1, then we'll get is 3, 0 is here, minus 3. So is it like here? So we are putting is here x equal to 0 plus 3y squared equal to 0. So we have basically 3y squared equal to 3. So like y power 2 equal to 1. So we could have plus minus square root 1. So which is plus minus 1. If y equal to 0, then from 1, we have like this 3x power 2 minus 3 plus 3 0 square equal to 0. So similarly, x equal to plus minus 1. So we have the stationary point here. A stationary point here. Zero, 1, 0 minus 1, and 1, 0, minus 1, 0. So here is a total four stationary point. Okay. Now we need to classify. We need to classify. So for the classify, we need to do the second derivative. Keep continue for this one. So for the classification, we need to find out at first f of x, x and f of y, y. Let's do it then. So look at that. We have f of x, this one. So if you derivative again with respect to x, that will give you 6x. And if you derivative this one with respect to y, that will also give you 6x. And we need to derivative fxy, so which will give you 6y. Okay. Now you need to find the determinant. It's like this way. You can write down d xy f xx times xy times f y and y x y minus f xy. So you need to plug all the values. It's basically this is a 6x, this is a 6x minus 6y squared. So you have 36 squared minus 36y squared. So remember that d is that part. Now we need to find out at if this determinant, we need to find out we need to plug 0, 1. This stationary point 0 and 0 minus 1, 1, 0 and minus 1, 0. The four different cases is here. And see this d is a positive or negative. So at 0, 1, d 0, 1 equal to we see is minus 36, which is negative. So this is a saddle point. This is a saddle point. 2 at 0 minus 1, d 0 minus 1, that also giving you negative is a saddle point. Same thing. Okay. Now at 3, it's like a 1, 0. Then d will give you is 1, 0 equal to 36. 1 square minus 36, 0, which is giving you 36 and then 0. So this is a f of x. When it's positive, then is a minimum point. When it's negative, then is giving you positive point, maximum point. So f of x and x 1, 0, 6, 1, that will be here. So once you have the positive, then you can see is here. So this is your min point. And number 4 is at minus 1, 0. So d minus 1, 0. Again, 36 minus 1 squared minus 36 is 0, is a positive. Now you need to find out y minus 1, 0. So is 6 minus 1 is negative. So this point is a max point. Max point. Now we need to classify this extraction point using the Hessian matrix. So what's the Hessian? How to find the Hessian matrix? Remember. So Hessian matrix is H x y f x x f x y f x y f y y. And this is a Hessian matrix. So now let's classify this stationary point using the Hessian matrix. So Hessian matrix x y h x y f x x f y y f, sorry, this is x y, this is x y, this is y y. So you have 6x 6y 6y and 6x. So at 0 1, the Hessian matrix will give you 0 6 6 0. So you have two eigenvalues, lambda 1 equal to 6, lambda 2 equal to 6. So have different sign. So we have here, we found fyy at this point is minus 6. Remember that. So this is fyy. This is 6x is 0 and 0 1. So is a lambda 2 is minus 6. So 0 and 1 here is a saddle point. As the eigenvalues have different sign. So similarly, you need to find all the Hessian matrix and their eigenvalues. So same eigenvalues you can find out the same as you have done in linear algebra part. 0, minus 6, minus 6, 0. So here is lambda 1 is 6 and lambda 2 is minus 6. So 0 minus 1 is a saddle point as the eigenvalues have different sign. This is, and then H10, that will give you 6006. So here lambda 1 is the same sign, is lambda 1 equal to 6, lambda 2 equal to 6. So they have same sign. So we can write down 1 0 is a minimum point as all the eigenvalues are non-negative. Similarly, you can say h minus 1, 0 equal to minus 6, 0, 0, minus 6. So here lambda 1, 6, and lambda 2 equal to minus 6. So in the positive is minimum. Remember that. Is a negative here, is the same. The same thing, but is a maximum point if they are non-positive. So minus 1, 0 is a max point as all the eigenvalues, you can see they are non-positive. Now we'll solve this one. So number 2, here's a 1, here's a 2. This one, to find the stationary point, again, to find the stationary point, you need to put fx equal to fy, fz. So you need to differentiate the function with respect to x, y, and z, and then equal to 0. So here, f of x equal to 2x minus y, equation 1. F of y is 2y minus x minus 3z, which is equation 2. Fz is 14z minus 3y. This is your equation 3. So to find the stationary point, we need to solve this system, which is 2x minus y equal to 0, minus x plus 2y minus 3z equal to 0, minus 3y plus 14z equal to 0. If you solve this, then you will get a stationary point. A stationary point 0, 0, 0. Now we need to classify. For classification, we need to do number 2. 2 is here. We need to build the Hessian matrix to classify this this problem, classify this one. So we need to build the Hessian matrix to classify the stationary points. Classify these problems. Okay, we need 6 second derivative due to the symmetry of the Hessian matrix. So we need 6. We need there's 6 second derivative due to symmetry of the Hessian matrix. Okay, so if you do this, then it's giving you 2 f of x, y. That will give you, basically, look at that is here, minus 1 f x z equal to 0, f y y equal to 2, fyz equal to -3, fzz equal to 14. So that will give you the Hessian matrix is here. So it's H equal to, first thing is this part. So we can write down 2. Second thing is -1. So we can write down -1. And third thing is a 0, like this, 0. So basically H is f of x, y, as f of x, f of x, y, f of x, z. And then is basically -1, x, y, f of y, y, and f of y, z, and then f of x, z, f of y, z, f of z, z. So this is the thing, the Hessian matrix is here. So we need to just plug that values accordingly. So we have is here the -1. This is 2. So you say 2 is here. This 2 is here. And these -3. yz -3. Here 0 -3. And then 14. This is the Hessian matrix. Then you need to find out the eigenvalues from this Hessian matrix. So we need to find out eigenvalues of this matrix. So which is determinant H minus lambda I. So this is a characteristic polynomial. 18 times lambda square, 15 and lambda plus 24 up to 0. We need to solve this characteristic polynomial. So after solving this characteristic polynomials, we can find lambda 1 approximately. This is 0.609. Lambda 2 is here 2.679, and then lambda 3 is here 14.7712. So if you look at that, all the eigenvalues are non-negative. All eigenvalues are non-negative. This means the stationary point is a minimum point. Now we'll solve the problem 4. The extreme values of the function subject to the given constraint using Lagrange multiplier. Here we need to consider this system f of x, lambda g of x, f of y, lambda g of y, and g of xy equal to its constant. So from here, you can see is we can write down 2x minus lambda. So this is f of x and this is g of x, you can say. So this is 2 lambda x minus 2y equal to 2 lambda y. and g of, x is like this. So from here you can write down basically g of x, g of y, and g of xy squared equal to 1. So this is equation 1, 2, and this is equation 3. So from equation 1, we have 2x minus 2 lambda x equal to is we have is 0. Then you need to the common factor from here, which is 2x and 1 minus lambda equal to 0. That will give you x equal to 0 and lambda equal to 1. If lambda equal to 1 and plug it in number equation 2, you could have 2y equal to 2y, which is 4y equal to 0. That's mean y equal to 0. And using 3, if you plug it here, using 3, then you have x equal to 0 and y equal to 0. So what will happen? If you using the y equal to 0 in equation 3, mainly equation 3. So what will happen? So x square plus 0 square equal to 1. So x equal to plus minus 1 square root of 1. So plus minus 1. Similarly, if you use if x equal to 0, then same way. So 0 square plus y square equal to 1. So we can find is y equal to plus minus 1. So the extreme points you have when is 0, x equal to 0, y equal to 1 minus 1. When y equal to 0, then x you will get a like this. So write down is here. So the extreme points are 0, 1, enter 0, minus 1, 1, 0, minus 1, 0. Now we need to evaluate the values. It's like f of xy. What? So evaluate fxy at this point. So f of 0, 1 giving you minus 1. F of 0, minus 1 is minus 1. And f of 1, 0, that is giving you 1. F of minus 1, 0, that will give you 1. So what will happen? The max values of 1 is occurs at this one. So, and that on this point, this 2 point. And the minimum will occur this point and that point. So write down the max value of f is 1 occur at 1, 0, minus 1, 0. And the mean value of f is negative 1 occur at 0, 1, and 0, minus 1. So this is the solution. So remember that for the extreme values, to find the extreme values, we need this system to solve the problem. Okay. Now, question 5. Find the second degree Taylor approximation of f of x, y equal to f of xy. So to solve these problems, we need JF and HF, Jacobian and Hessian. So fxy will give you ye power xy and f of y, xy x e to the power xy. So jf will give you y e to the power xy and x e to the power xy. So this is your JF, Jacobian. So Jacobian at this point is JF 0, 0 is a 0, 0. So f of 0, 0 e to the power 0 equal to 1. So we need to find this one from this one, f of x, I mean you need to derivative double times with respect to x. So then you will get y squared e to the power xy. If you do y, then x squared xy. Look at that, it's here. And we need xy, x comma y e to the power xy plus y x e to the power xy. So 1 plus xy e to the power xy. And now we can build the Hessian matrix from this. So Hessian HF, remember f of xx, f of xy, f of xy, f of yy. So I'm going to the next phase is here, continuous. HF is now finally y squared e to the power xy, 1 plus xy e to the power xy. Same thing is here. And here x squared e to the power xy. So this one. So HF at 0, 0, we could get is like a 0, 1, 0. Sorry, this is 1, 1, and here is 0. So we have this session. Now we can write down the function f now f xy f of 0, 0 languages multipliers. So f 0, 0 and x minus 0, y minus 0 plus 1 over 2, x minus 0, y minus 0, Hessian matrix 0, 1, 0, 1, 0, and x minus 0, y minus 0. This is the approximation. We know this one is a 1 plus 0, like this 0 is here. This is so this is a vector. So we have x and y. That's 1 over 2, x and y, 0, 1 over 0 is here, x. So finally, if you simplify this one, so that will give you, this is a 0, so we know that 1 over 2, xy, and yx. So finally, 1 plus 1 over 2, like a xy plus xy. So that will be giving you x plus xy. So this is your answer. So question number 6, do 3 iteration of the gradient descent algorithm on fxy equal to x power 2 plus xy, and it's starting from 1 comma 1 and the learning rate of alpha equal to 1. So the solution is here. in this case, we need to find the gradient first. So let's find the gradient. Gradient first. So which is lambda f x x1, f1 x1, 2x plus y, and x then is x naught and y naught, x0 and y0. Here is a starting point. This is the initial point 1 and 1. So, and you can see from here x1 and y1, and that will give you x naught and y naught minus 1 lambda f x naught and y naught, 1 and 1 minus, if you plugged these values is here, that will give you, I mean, it's here 3 and 1. So you have finally minus 2 and 0. And you got this 1 minus 2, 0, or you can say minus 2, 0 is here. Similarly, you need to find x2 and y2, 3 iteration, equal to minus 2, 0. I mean, this is x1 minus 1, now this point, f x1 and y1, basically. So is here minus 2, 0, and you can find minus 4, minus 2, so that will give you 2 and 2. Similarly, you can do is here x3 and y3. So you need to use x2 and y2 is here, then 1, now f 2, 2. So 2, 2, 6 and 2 is here. Basically, that will give you is minus 4 and 0. So this question is likely theoretical. So maximum likelihood estimator of a Bernoulli parameter. Suppose that n independent trials, each of which is a success with probability p, are performed, and what is maximum likelihood estimator of p. So in that case, we need to consider the random variable. So let's consider the random variable x1, x2. So where xi equal to 1, 0, if 1, when, if trial I is a success, otherwise 0. So these are n independent trials. There are independent trials. The probability mass function is PMF of each random variable with px I equal to 1, p. So 1 minus p xi equal to 0, which can be expressed as like a p xi equal to x. So px power 1 minus p power 1 minus x, where x equal to 0, 1. So the important thing is here, this P, the parameter that we want to estimate using the data, this parameter. That we want to estimate using the given data that we have. Okay. So we have is here, if x equal to 0, then pxi to 0, p of 0, 1 minus p, 1 minus 0. So here you can see is 1 minus, this is equal to something, remember something power 0 equal to 1. So, and this is 1 minus p is here. If x equal to 1, pxi equal to 1, p1, 1 minus p, 0 is here. So this is a p. So, I mean, you can do that this way. Let's go to the next page. So consider that we observed xi equal to xi at each experiment. So consider that we observed xi at each experiment. So which is xi belongs to 0, 1. So our data should be like x1, x2, xn, like this. So as the experiments are independent, so we can write down like this as the experiment are independent. So f of x1, x2, xn, there is a partition. That's mean the function x1, x2, xn given p. So this is a probability of x1 equal to x1, x2 equal to x2, and dot 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 xn equal to xn. This is a given probability p, given event. So we can write down like this way: p x1 equal to x1 partition p. P is here x2 equal to x2 partition p. Dot dot dot. P xn xn equal to xn partition p. So here p of x1, like what we have found, is here, and 1 minus p, 1 minus x1. Similarly, p x2, 1 minus p x2 dot 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 p xn, 1 minus p xn. So we have like this p x1 plus x2 is here, this one, that one, that one. So plus dot 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 dot, dot plus xn, and 1 minus p 1 minus x1 plus 1 plus x2 plus dot 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 plus 1 minus xn. So we have p summation of xi I equal to 1 to n. Here 1 minus p n minus, so 1 plus 1 plus 1 is a nth basically, and minus summation is n I 1 to xi belongs to 0 and 1. So now we have finally look at that this side, why we have started. Now we are here. Now L of P, L of P, log of f x1, x2, dot, 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 xn, partition P. So log of, you need to plug all the values now is here that you have found this part. P summation of I equal to 1 to n xi 1 minus P n minus summation to 1 xi. So log of P summation n is equal to 1 to xi plus log of 1 minus P. I mean, this is a formula. This, if you have the like log of mn, you can write down log of m plus log of n. You can write down the same formula we're going to use here. So n minus I equal to 1 to n xi is here. So summation n I to n xi log of p. So if you have is like a log of ab, you can write down b log of a. You know that. So same is here in minus summation or I equal to 1 to n xi and log of 1 minus p. Now we need to find the L prime p. Now we need to find L prime of p equal to 0. So that's means we need to derivative the L with respect to p. So if you derivative with x with respect to p, then I'm going here dl and dp. Look at that n I not to n is here xi 1 over p plus n I 1 to n xi is here minus 1 over p is here. So you need to if you derivative with log x dy dx, that will give you 1 over x. Remember that. So same thing we did it is here. This is a constant. We are dealing is this part, this side and that side. Okay. So now finally we have summation of xi I equal to 1 to n and p is here minus n summation I equal to n xi and 1 minus p equal to 0. So as we said, we need to find this part. So we found dl and dp and we need to put it this. So this we can write down like this. So look at this is here xi and p is here and n summation xi 1 minus p. So we just need the cross multiplication is here. So p n minus summation of xi and 1 minus p summation of xi. So pn p summation of xi p summation of xi. So look at that. This one and this one is cancelled. So finally you have p equal to summation of xi divided by n. So we can write this p have summation of n I equal to 1 and xi divided by n. Hence, this is your the MLA is like MLE, maximum likelihood estimator, MLE. So we can finally write down like this. So hence, the MLE of unknown P is the mean of the observation. Okay. So again, look at that. We started from here and then we keep continued. We find the probability, the conditional probability, because this is the independent, and then we have found this part. So let's say this is P by B. You can write down basically P, B intersection like this, P of P. So here, if this is, this is one of the condition, this is conditional probability, and if B and P is independent, then their probability, the multiplication between their probability should be the same. It's like this. So that's why we just multiply this here. This is multiplication is here. So then we found this part, and this is LP. LP is a log of fx1, x2, x and p. We just plug the values is here, and then we derivative L with respect to P is here, and set equal to 0, and then we found this thing. So the MLE of unknown P is the mean of the observation. So